Welcome back as we begin part 2, introducing continuous process systems and proportional control action. In our fictitious company, let's suppose the demand for their products increased to the extent that the batch processing method just wasn't able to cope. The management and engineers decided that a relatively cost-effective solution would be to install a continuous process system. In basic terms, the new continuous process was to rough blend the raw materials through agitators, then feed the homogenized mixture through a heat exchanger unit for the blending process. Finally, the blended product would be fed to 2 automatic bottling lines, either of which could be run independently depending upon the demand requirement. Now, let's suppose the engineers decided to maintain the original on-off control unit. However, they replaced the original steam valve with a larger unit to cope with a larger steam flow into the heat exchanger. Here's what is likely to happen. On startup, the temperature sensor, as before, will signal a low temperature, and the set point controller will cause a full valve opening. The product will now heat up and the temperature will rise. When it reaches set point, the controller will shut the steam valve just as it did on the batch system. But a look at the temperature record will show us that we have a big problem. Typically, the temperature might rise as high as 90 degrees Celsius and then drop back to around 70 degrees Celsius in a cycle. In other words, our product will be off specification and again, worthless. Let's study why this is likely to happen. Remember that in our old batch process, we had a large container in which the product was blended. We can liken this to an electric bar heater that is trying to warm the air in a room. Should one decide to increase the heating, then we would set the heater to its high setting, which then takes quite a while for the effect to be felt, owing to the volume of air in the room. In a similar fashion, releasing steam into the steam jacket results in a slow temperature rise of the product. But a different situation exists in a continuous process, which can be likened to a hairdryer. When the hairdryer is set to its high setting, the user feels the temperature change almost immediately. In similar fashion, an increase in steam volume through a heat exchanger will result in rapid warming of the product in the system. What is clearly required is a method of being able to open or close the steam valve gradually, and then to hold the valve in a position where the volume of steam entering the unit can be kept at an optimum level. In other words, we must be able to position the valve anywhere between closed and open, according to the temperature requirement. To achieve this in a continuous system, we require a device known as a proportional unit, something that responds to a given measured value, in our case, temperature. Our controller must therefore be equipped with the first element for a continuous system, namely a proportional unit. In order to understand the principle of proportional control action, let's use an illustration. Here we have a balanced beam, where the pivot point, or fulcrum, is centrally located under the beam. We'll represent the valve's open and closed position on the left, and on the right we'll represent a signal process variable, namely temperature. In our representation, a drop in temperature will result in an equivalent change in the valve's position. That is, a temperature drop will result in an equivalent or proportional valve movement towards its open position. Likewise, a temperature increase will result in a proportional valve movement toward the valve closed position. In other words, the opening or closing of the valve is in proportion to the size of the change in our variable, that is, the temperature. Now, let's upset the balance by repositioning the pivot, for example, to the right. We now see how a small temperature change will result in a relatively large valve position movement. We call this situation high gain. Conversely, should we shift the pivot over to the left, then we see that a large temperature change will result in a small valve position movement. We call this low gain. A proportional control device, sometimes called a gain control, works on the principle we have just described. Selecting a high gain will result in a large valve position change in proportion to a small temperature variation. Let's overview the system operation, assuming that a proportional action control unit has been installed. Now, whenever the indicated temperature moves off the set point temperature, the amount of error is detected by a special circuit controller called a comparator, also known as an error detector. If the sensed temperature is above set point, then the comparator generates a positive error signal. Likewise, when the sensed temperature drops below set point, then a negative error signal is generated. The value of the error signal, whether negative or positive, is directed to the proportional unit where modification of the signal is made according to the gain set position. A resultant output signal is sent by the proportional unit to the final control element, namely our steam valve controller, where the valve is set to the relevant opening position. To assist the operator and engineers, a valve position indicator is normally fitted onto the control panel, where, at a glance, the relevant position of the valve opening can be assessed. The first major modification to the original on-off controller has been made. Now, on startup, the controller signals for a full valve opening. The inrush of steam results in a temperature rise of the product, all the while being monitored by the temperature sensor. The error detector modifies the signal and causes the proportional unit to regulate the valve's position effectively. Now, when the set point temperature has been reached, 80 degrees Celsius in our example, the steam valve will be set to the position that provides the correct steam flow necessary to maintain the blending process within allowable limits. Our system, however, is not yet perfect, and we'll discuss why after the break.